All right, so we are ready to get started with on a day 9 in just a few minutes, in about 5 minutes. So we're gonna have our exam 1 on this Wednesday, and I already sent out notifications or announcements regarding the time slot for each person. Um, so I'll be a little bit busy on that day because there are 3 time slots in order to cover everybody. But it's okay, I just want to be accessible live, during the exam. So when people need clarification, I'll be there to answer questions. So it's not going to be a online, test like some of your other classes, I suppose. And we got some questions today about the lab, particularly question 4 and 8. So I'm going to work on all of those questions today first, and then we'll start to talk a little bit about the exam, like what kind of question, and also how to prepare for the exam. All right, we got 4 minutes remaining. The YouTube side is streaming already. Let me just double check. Yep, so that's streaming already. So I'm starting the recorder a little bit early today. Since we got some time and no one is asking any question, I'm going to take a little screenshot, take a little picture of how I set up my workstation. All right, so let's see. There we go. So that's how I set up my workstation. The screen itself, the main screen, is a 4K monitor. I think it's a 28-inch. And then at the lower right-hand corner, that's my tablet PC, which is in the tablet mode. And it also has a kind of wedge, after it's folded. So this way, it's angled a little bit, so I can write more easily on it with my tablet stylus. And my 4K monitor is already filled with stuff too. Alright, so we got about a minute and 40 seconds to go. If you guys have any questions to ask, now is a good time, or at least put it onto the text channel so I know what topics you guys want me to go over. And then Sakio is typing. Alright, we got 45 seconds to go. Alrighty, it's 9 o'clock. Let's go ahead and get started. Good morning and happy Monday, everyone. Um, because Sakio asked, not Sakio, Martin asked about questions 4 and 8 in the lab. So just kind of want to go over the lab itself a little bit because I think some of the terms may be a little bit confusing. So here's question number 1. Consider the base 10 number as follows in scientific notation. So it was pointed out to me that this is technically not in scientific notation because in scientific notation, this portion here, which is called the coefficient, is supposed to be normalized, and this is not normalized. So when I say it's scientific notation, it simply means that there's a coefficient part, and there's an e to specify whatever follows is an exponent of 10. Okay, so that's basically what I consider a scientific notation. So it says right here, it is conventional to normalize the mantissa. The mantissa is actually referring to this part here. So it's basically the coefficient. So in my notes, when I mention mantissa, it is used interchangeably with what some of the other texts would call the coefficient. Now it is actually the mantissa once it is normalized, but when it's not normalized, it's technically not the mantissa. So if you look up the definition of mantissa from Wikipedia, you will find out what that means. It's the fractional part, but it's not the fractional part of the coefficient. It is the fractional part of the log of the value using base 10, for the log. So, so it is still appropriate in this case, even though the best term to use is just the coefficient. So it is greater than or equal to 1, but less than 10. If we are to normalize the mantissa, what is the new exponent so that the notation maintains the value it is representing? In other words, I need to move this point right here so that it is between the 8 and the 9. By doing that to the coefficient itself is going to be 1/100th of what it used to be. And I need to compensate for the reduction of the value because I moved the decimal point. So that means, on the exponent part, I have to make up by increasing it by 2. So in this case, the answer is going to be negative 31 because negative 33 plus 2 is negative 31. Do we have any questions about this before I move on? Okay, all right. So here's question number 2. It says, consider the value represented by the following base 10 number. What is the exponent of the largest power of 2 that is less than or equal to this value? In other words, find the largest integer p such that 2 to the power of p is less than or equal to 280 times 10 to the power of 4. So the first thing I want to kind of remind people, when we have e4 in this case, it is not saying the natural log constant to the power of 4. That is not what this notation is for. This notation is indicating that we have a power of 10, 10 to the power of 4 in this case, as the magnitude of the number. So there are several ways to work out this problem. You can definitely use a spreadsheet if you want to, or you can just use a calculator and rely on the log function to do it. So I'm going to show you guys how I would do this. I'm just going to use OpenOffice Calc, which is just a spreadsheet. So I'll put it into view right there. And the idea is to take the log and to find out how many bits we need to represent this value. Alright, so there's no log of 2 in most spreadsheets or most calculators, but that's okay because all you have to do is to say log, I cannot remember the concept, I think it's 280 E4, and oh, actually, in this particular spreadsheet, you can specify the base, which is probably an optional parameter. So I can just say log of 2, and we can see it's 21.41. Since we want 2 to the power of p to be less than or equal to this number or this value, and we also want p to be an integer. So that means I have to use 21 in this case as the answer. Do we have any questions about number 2? Okay, questions. We're moving on. All right, so here's question number 3. Question number 3 is asking about the base 10 representation of the value that is in return represented by the following base 2 number. So this is a base 2 number. So this one here, right here, is 2 to the power of 2, which is a 4. This one is 2 to the power of 0, which is a 1. And this one here is 2 to the power of negative 1, which is a half. So in this case, we have 5.5 as the value. Do we have any questions about number 3? Okay. So if there are no questions, I'm going to move on to number 4. So number 4 is a little bit tricky because I want you to find the closest base 2 representation to this particular value v, which is currently represented in base 10. So in this case, I want 5 bits to the left hand side of the point and 3 bits to the right hand side of the point. This value, which is 13, the integral part is 13. 13 is 8 plus 4 plus 1. So it is 0 because there are no 16s. 1 8, 1 4, 0 2s, 1 1. So now here we are moving on to the fractional part, which is going to be a little bit tricky one. For this one, it's not too tricky, but for some of the other cases, it can be a little bit trickier. So we look at 0.65 in base 10, and then we ask how do we approximate the value 0.65 in base 10 by basically negative powers of 2, a sum of negative powers of 2. So that's the question. So we definitely have a half, okay? And now the question is, do I want to have a quarter? So a half plus a quarter is 0.75. A half plus an eighth, on the other hand, is 0.625. So now you have to choose between those two because the actual value we want to represent, which is 0.65, is between those two values, but is closer to one of them, which is the 0.625 in this case. So in this case, we have none of the quarters and one of the eighths. And I think this is what threw off some people because they think that we just want the binary representation that is just less than the base 10 representation, but that's not what the question is asking. The question is asking what is the base 2 representation that is closest to the value that we want to represent. So sometimes that value can be just a little bit over the value in base 10 and not always less than. So I think that is all that I want to demonstrate. Is that okay, Martin? That I do not go through number 8, or do you want me to go through number 8 too? Because these numbers are different from yours. All right. So let me just kind of submit the whole thing. Because when you submit, the answers are going to be, it will truncate it. But the truncation should not affect what is considered correct and what is considered wrong. So for question number 1, I got 1 out of 1 point. Question number 2, 1 out of 1 point. Question number 3, 1 out of 1 point. And then for question 4, we can see the leading 0 is gone and they put in a comma over here. But still, it gave me 1 point out of 1 point. Okay, so Mantissa, what do you want me to do with 13.067? Can you do one that start from 0.759? Well, the question is, if you have, oh, excuse me, I keep rubbing the windscreen of my mic. All right, so let's take a look at that number. Okay, so Mantissa wants me to take a look at 0.759. So the question is, what is if you can only have halves, quarters, and eighths, and you can either have 0 or 1 of each, okay? How do you make up a sum out of those powers of 2, negative powers of 2, to make up for the quantity or the value that we know as 0.759 in base 10? That is the question. So I want you to kind of think about it first, because it's really the same process for the integer part. It's the same process. You got a half, you can have 0 or 1 of those. You can have 0 or 1 of the quarters. You can have 0 or 1 of the eighths. So given that is the option, what is the best approximation of 0.759 in base 10? That's really the question. So which one is it? Because you gave me 3 values already. One is 13.06. I'm not. I don't know what you want me to do. You're now giving me 4 values. What do you want me to do? Please present a question or a statement, not just a number, because I don't know. If you just give me a number, I don't know what you want me to do with it. We probably need to take this one offline, after the class is over. All right, so we'll do one more. We'll do 13.06, and we are going to move on. You're more than welcome to use my office hour for any additional discussion. Okay, so for 13.06 in base 10, how do we approximate that value using powers of 2? So let's do the integer part first, okay? All right, so I'm going to write this down here, 13.06. And we want to make this up only using 1 or 0 of each power of 2, okay? So we can say, oh, what about 32 and 64? Those are all 0, okay? No problem with that. So we want an 8, we want a 4, that makes up 12, and then we have a 1 that is remaining. So now we got 0.06 left, right? So with 0.06 left, do we have a half? Is a half even close to it? Okay, no, it's not close, right? So we do not have a half. What about a quarter, which is 0.25? If I have to choose between none of the quarter and one of the quarters, none of the quarter makes sense, because one of the quarter is already a lot more than 0.06, but none of the quarters is really close to 0.06. What about the eighths? An eighth is 0.125. So now you have to ask the question, is 0 closer to 0.06, or is 0.125 closer to 0.06? What do you think, Mantissa? This is a question I'm asking back to you, because ultimately you're the one who needs to understand how to make that decision. Do we have 0 of the eighths, or do we have 1 of the eighths? Is 0 closer to 0.06, or is 0.125, which is 1/8, closer to 0.06? That's right. So that means this number would be represented by 0.1101.000, because we do not have a half, we do not have a quarter, and we do not have an eighth. So there. Okay. All right, so I'm done with reviewing the lab. If anyone needs any more help with these concepts, we can do it during the office hour time, okay, or the lab time if no one is asking questions related to today's lab. So we're going to move on, and obviously sometimes I forget what I'm supposed to say, so that's why I sent you, a little agenda for what we'll be talking about today. So we'll talk about exam 1 now. So in exam 1, the first thing is to talk about the process. On the day of the exam, on Wednesday, I know who has already expressed exclusions of which time slot, and accordingly, each person will be using the first of the 3 time slots that I made available, which is from 9 to 10:30, from 10:30 to noon, and also one more from 9 to 10:30 p.m. Of those 3, okay, you are going to go to the first one that you're available for according to the form you turn in. If you do not turn in any form, I make the assumption that you are available for all time slots. Then you're going to go to the first time slot, which is from 9 a.m. to 10:30 a.m. Okay, does everybody understand which time slot you're going to use for the exam? Or I should ask, is anyone not clear which time slot you're assigned to? So we've got David typing. Oh, I got 1 p.m. Let me check out that. Okay. All right. So you can still correct your availability. Just make sure that you indicate what time slot you cannot make it. Okay. I'm not asking for your availability. I'm asking for your unavailability. So whatever block of time you cannot make it, you can go ahead and adjust your submission to the form, and I'm going to recompute to see whether those 3 time slots are correct or not. Okay, all right, excellent. Yes, Richard. So what you do is you have to review what time slots you have marked unavailable, and I got 3 time slots. Okay, one is from 9 to 10:30. So if you have not marked that time slot as unavailable, that is your time slot. Now, if you mark 9 to 10:30 a.m. as unavailable, but 10:30 to noon as available, that would be your time slot, which is the second time slot. Now, for people who marked from 9 to noon, both as unavailable, the third available time slot is 9 to 10:30 p.m. Okay, and according to the responses from all people who turned in something, these 3 time slots should cover everybody in the class. And people who did not turn in any form is implicitly saying they are available for any time slot, so they're all by default going to the first time slot. Okay, Sakir is typing. All right. So if we accidentally mark it as unavailable, you can go ahead and correct it. So go back to the form, which should allow you to change your response. So go ahead and fix it and then resubmit it. All right. Okay, so assuming this is okay, what's going to happen is I will pre-share a Google document that contains, you're welcome. So I will pre-share a Google document that has all the questions to you. Okay, so basically as soon as you get that shared document, you can get started working on it, which is going to be a little bit before 9. and then at 10:20, not 10:30, but at 10:20, I'll run another script to unshare the document. So for people who want to really push it to the end, they may be typing when the unshare event happens, because I will start the script at 10:20. The script may take 1 or 2 or 3 minutes to finish. So that means some people might be able to push just a little bit more into the document, but there's no guarantee of how much. Okay, and I cannot respond to people who use Discord and text me, but can I just get a few more minutes? The answer is no. So how do we find it in our apps? I'm assuming Catherine is referring to the shared document. So whenever I share a document with you, which is to your apps.losrios.edu account, your Gmail will receive, there will be a message to your Gmail that says that I have shared a document with you. So you can use that to find out. The alternative, okay, is to go to Google Drive and have Google Drive to list documents that are recently shared with you, and I think it shows up that way as well. Okay, so very good. So once the document is shared, you can get started with it. There's no need to write down your name because I know which document is shared with which individual. So there's no need to write down your name because I know, who is getting that particular document. So you can get started right away. Because it's a Google document, you can use all the fancy formatting that you can do with Google Doc. Some people even do certain things on a piece of paper, and then they take a picture of that, and then they paste the scanned picture into the Google document. Even that is okay. Okay, for one particular question, if you say, I can't just type the answer out, because it's kind of more graphical. I need to draw arrows and lines and stuff like that. You can do it on a piece of paper, and then take a picture of that, and then upload and include that picture into the Google document. Now there are a few more steps, to do it that way, but if that doesn't bother you, hey, it's perfectly okay. The exam is going to be open book, open notes, and in a strange way, open internet. Okay, it's open internet only to the point that there is no collaboration of any kind during the exam. So if you find that one question is about binary, say, addition, okay, and the question is giving you the x and the y and is only asking you about the sum, and you found this really, really cool binary addition app on the internet, you can actually use it to do the calculation and come up with the answer. But that's usually, in practice, is not going to be very helpful because I am going to ask questions where an online calculator probably cannot solve the problem, because I need to know that you know how to solve the problem and you understand the concepts underneath the question. I'm not trying to assess your ability to Google for a tool to do it for you. Okay, so that means don't count on having online calculators to help you figure out the answer, and try to make sure that you understand the concepts themselves and be able to apply the concepts to problem solve something that you probably have not seen in the labs. Okay, and I do it intentionally because I don't want people to just kind of reapply what they have done in the lab. I want people to demonstrate that they actually understand the concept and be able to utilize the concepts in a in the question that's asking about the same thing but differently. Okay, so now we are moving on to the concepts involved in the exam. So the gates are within the scope. Okay, some of these I have not yet decided how to ask specific questions about, and they may not have any questions about that. Okay, so I may not have one question that is specifically about all the different gates that we have talked about. Base conversion is kind of important, so you can kind of count on there will be base conversion related questions. I know there are online calculators for base conversion. In other words, you can type in a number in a particular base, it will give you the base 10 representation, or you can type in the base 10 representation and give you the representation. There we go. So and it will give you the representation in a different base. So you can probably count on not seeing questions that are straightforward like that. Okay, I probably have to find a way so that I can still quiz you on the concept to make sure that I can see that you understand the concept, but it is not something that a online calculator can do it directly. So you can probably count on that. So you also want to be able to have problem solving skills. I would be testing your problem solving skills in the exam as well. So specifically with all the different bases, base 2 is important. So with base 2, in addition to conversion between the bases, I also want to see that you know how to add and subtract binary numbers. So just as I said a little bit earlier, this is not about assessing whether you can find tools to perform binary addition and subtraction. This is about whether you understand the concepts of binary addition and subtraction. So I'm going to ask you certain questions, to see whether you understand that or not. So we have the borrow or carry look-ahead mechanism, which is a way to speed up binary adders and subtractors. Compared to carry ripple adders and subtractors. So those are a little bit harder for me to ask questions about, because either they are too complicated. I cannot ask you to give me a logisim file for a 6-bit carry look-ahead adder. That's just going to be it will take you a lot of time to do that. So I have to kind of look at how much time a particular question needs in order for you to answer, as opposed to can I still see that you understand the concept. Okay, so some of these questions I have no idea yet how I'm going to ask it this semester. But these are within the scope. These concepts are all within the scope of exam 2. We are also including in the scope of signed versus unsigned integer interpretation of a bit pattern. So if I give you 5 bits, okay, 5 zeros and ones, and I say, hey, what is the value of this, if you want to interpret the bit pattern as a signed integer, okay, I want to be able to see that you understand the concept and be able to figure that out. Or I can give you an integer value, okay, and I say, okay, here's a value, okay, 46 or something like that, and I want you to represent it as a 6-bit 6-bit unsigned integer. So I want to see that you know how to do that. Unfortunately, there are also calculators online that can do all of this for you. So and some of these calculators can even show you the steps, so you can just kind of copy and paste everything from the calculator into the question. So that means I have to find a way to ask these questions in a way that the calculators cannot do. And the last topic, or the last group of concepts for this exam are related to comparison. B is the overall borrow in a subtraction. S is the sign of the difference after a subtraction. O is the overflow, and then L is the exclusive OR between the sign and the overflow. So these concepts are already defined in the modules, okay? But I need to see whether you know how to apply these concepts. So the definitions are definitely, okay, that can turn into a meme. The definitions are definitely important, so you want to know what the definitions are. Now, if you cannot remember all the definitions, it's no big deal, okay? You can actually prepare your own document so that you have a little quick index into all of the definitions. But from the definitions, you also need to know how to apply the definitions and the concepts to solve these questions. So do we have any questions about exam 1 based on what I have just talked about? And please do not ask whether it's going to be hard or not, because I cannot assess the difficulty of my own exams. Okay. L is less than from the signed perspective. It should be in the module. Oh, okay, there you go. I'm waiting for some additional questions that are being typed, so okay, I'm still waiting. Just double checking to make sure that my Discord is still working. There we go. All right, so here's a question. So for these definitions, this is what Martin typed. Can we make sure that we had homework or classroom problems to look back at? No, that is not going to be guaranteed. I would not want to figure out how to solve a circuit or for a definition we have not actually worked on yet. So the idea is you already know the concepts. The lab have already exposed you to the concept and you have solved some problems related to the concepts. Oh, I did not share my journal notes. I'm gonna share that later today. Someone can remind me to do it today, because there will be some additional material for today. The one from last week is still in the document, so you're gonna get everything up to this point. So getting back to Martin's point, okay, is the concepts are there. Okay, we have individual homework to deal with the concepts. But the problem solving part can be new. Okay, in other words, you have to apply the same concepts that you have already practiced using the lab, but in a new way to solve a problem. That is kind of the nature of those questions in the exam. So you won't encounter new concepts. I'm not going to define a new formula or new equation or a new bit of some kind, but you will have to solve something in a slightly different way. Okay, all right. So let me show you what I mean by that. Okay, I'm just going to show you an example. And looking for journal. There we go. All right. So we have already done binary addition. Okay, so let's go ahead and review binary subtraction first. Okay, so let's take a look at one. Oops. Okay, I need to fix this first. Give me a moment. All right, so that should fix it. All right, so let's check out 1001 minus 0111. Okay, so in binary addition, okay, we know how this is the x, this is the y, this is the q, this is the t, and this is the d. Okay, so all of these rows are defined. So what I mean by definition is basically saying, okay, we know q is the result of adding the x and the y bits, and so qi is the result of xi, yi, which in this case we also know it is also known as xi exclusive OR with yi. But we also talked about how to express this without using exclusive OR. So without using exclusive OR, this becomes the negation of xi and yi, or xi and not yi. Okay, so all of these are in the notes. Okay, and none of this is new stuff, right? So as a result of the definition of what qi is, I can now see, okay, 1 exclusive OR with 1 is a 0, 0 exclusive OR with 1 is a 1, 0 exclusive OR with 1 is a 1, 1 exclusive OR 0 is a 1. Okay, so now we have to come up with the t bits, okay, the take bits or the borrow bits basically. we know the least significant borrow bit is assumed to be a 0. So now we look at this and go like, okay, this is an easy one. 0 minus 0 is just 0 to get to the difference. But how do I get to the next borrow bit? So now we have to look at the other definition, which is ki plus 1 is the borrow of xi, yi, or the borrow of qi, ti. So now we want to look at this and go like, okay, looks like we need another definition, right? So the definition of b of xy is not x and y. That is in the notes. Don't I mean t? Yes, Catherine is correct. I meant t. In my mind, t and k are really the same thing, so sometimes I use the wrong notation. There we go. It is t. Correct. Thank you. Yep. Okay. So now, so when we look at this is the definition. So from this particular definition, we say, okay, not 1 and 1 is a 0. Not 0 and 0 is also a 0. 0 or 0 is a 0. So we put a 0 here. So now we have 1 minus 0, which is a 1. So now when we need to determine this, we look at not 0 and 1. That's a 1. Oh, but it's an or, so if I have a 1, I can put a 1 already here. 1 plus 1, or 1 exclusive or with 1 is a 0. So now we need to figure out this guy. Not 0 and 1 is a 1 already, so we put a 1 here. 1 exclusive or with 1 is a 0. So now we need to determine this guy over here. With this one, the last borrow, the overall borrow, we can see that 1 minus 0 is, okay, let me rephrase it. Not 1 and 0 is a 0. Not 1 and 1 is also a 0. So we got 0 or 0, so that means this is a 0. So this is the quote-unquote typical way to make use of the definition to go forward. Okay, so let me move this a little bit here, down here. And this time I am going to just write down 1001 minus, and I will leave this blank. So the entire row y is blank here. And I'm going to leave the row q also blank, but I will keep the t row around. So I have 0, 1, 1, 0, 0. And I'll keep the d row around as well. 0, 0, 1, 0. Okay. So now I'm asking you to figure out what the blanks are in this case. All right? So this is one form of question where I'm still asking you, I'm still trying to assess whether you understand the concepts or the definitions. The concepts or the definitions, let me scroll back to the right point here. So the concepts or the definitions that I want to ask you about is this stuff over here. Okay? But you have to apply those definitions, which is knowledge, in a different way to solve the new problem. So how do we solve the new problem? Well, let's try to figure this out. Okay? So I'm trying to demonstrate, how to solve a problem when you have not seen it before. Okay, so how do you approach this thing? And this is constraint-based thinking. I would call this constraint-based thinking, which is looking at what is given to you, and then you look at what you need to figure out, and you ask, okay, how do I restrict this value to only one possibility? Okay, I know each one can only be a 0 or 1, but how do I know which one it is? So as it turns out, this one is actually pretty easy, okay? Because to figure out this particular bit here, how do I figure it out, right? So we know, okay, this is y, this is q, this is t, right? So we know that d is the exclusive OR between the q and the t. We know, okay, put it index in the wrong place. We know this, right? Okay, so if I know this already, and I know that di is a 0, and I know qi in this case, ti in this case is also a 0, how do I figure out this guy over here? Well, what do you guys think? Because because this is not about knowledge. We have defined what is exclusive OR. Catherine got it. Okay, it has to be a 0. But how do we know it has to be a 0? Because if you plug a 1 in, it does not work. So it cannot be either 1, it cannot be a 1, and because each bit or each digit can only be a 0 or 1, it has to be a 0 in this case. You can also look at this from the perspective of a truth table. So if I look at the truth table, and I'm going to use ABC in this case, A, B, and then A exclusive OR B. So this table is pretty easy to define, and I'm pretty sure I have shown this table several times already. Okay, there we go. So those are the 3 rows. Okay, so with this particular problem, we are saying that we know B is a 0. Okay, there are only 2 rows where B is a 0. Let me highlight those 2 rows. So B is a 0 in this row, and B is also 0 in this row as well. So now we know that we know the answer has to be one of these 2 rows, right? Because of this 0 over here. This 0 over here locks down what B can be. But this 0 here, which is the result of the exclusive OR, is going to lock down this column here. In other words, I'm looking at these 2 rows and I'm asking which one has B being a 0 but A exclusive OR B also being a 0. This is the only one, because the other one has the result being a 1, so this has to be the only one. But if I look up this one and I ask what is the A that is causing this to happen, if I know that B is a 0 and A exclusive OR B is also a 0, what is A going to be? Now we know that we have locked down the value of A. Now, this is not binary addition or binary subtraction specific knowledge. This is really just constraint-based thinking. It is a technique, okay, but it is not. It's not. I wouldn't call this knowledge. Okay, I call this problem-solving skill. And I didn't teach anyone this. Okay, and some of you figure this out on your own. And that is what I will be testing as well in the exam, is based on the knowledge that we have already talked about in class. You still need to apply some problem solving skills on these questions in order to solve the problem. So do we understand the nature of the questions that will be in the exam? So it's the same kind of knowledge, it's the same kind of concepts, but it will be asked in a way such that people cannot use a calculator online to do it, and people actually have to do it on their own and demonstrate that they actually understand the concepts and understand how to apply the concepts to solve the problems. So are we good with this or not? No questions? All right. All right, so is this example doing okay? I mean, is everybody kind of understanding my point? All right. Hope so. Okay, very good. All right, so given this is how I'm going to test you, okay, how do you prepare for the exam? Okay, Richard was typing. Not sure whether he's still typing or not. Okay, so the question is, how do you prepare for an exam where it is not only asking, it's not just testing your knowledge, nor the procedures or processes that I'm not asking you to replicate processes from the lab or from the notes. Okay, so how do you prepare for an exam like this? Does anyone want to share? Studying the concepts. Okay, very good. Okay, so what do you mean by studying the concepts? Practice problems. Okay, so there's a practice problems are good for verifying that you understand the concepts. Okay, so it is good. How? Aha. Okay, so Richard says how Q and T works. In other words, how do we define those terms? Okay, so the first part, okay, is of understanding of preparing for an exam like this is to make sure that you are crystal clear on the concepts. Okay, what exactly is Q? Okay, so you go back to the original edition over here. What exactly is Q? Okay, Q is really just the exclusive OR. Okay, it is representing the result of an addition. Okay, what about T? T is representing the borrow of a subtraction. Okay, so I'm breaking up a single digit subtraction into its result, which is Q, which is done by exclusive OR between the X and the Y, and also T, which is based on this definition over here. Now, when you study, you don't need to memorize this, okay? Because it is already defined. It's an open book, open notes type of test. So don't try to memorize things, but instead understand what it is representing. Because what this is representing is, if I want to look at, I'm just going to use a different color to highlight. So if I want to look at this particular carry bit here, okay? I'm trying to figure out how can we determine that particular carry bit. Well, this carry bit can have a carry if I have a borrow from, I mean, not, okay, I'm using carry again, but when I said carry, I actually meant borrow. So when we have x minus y, that can contribute a borrow here. However, when we have q minus t, that can also contribute a borrow over here. That is why the borrow function, or the t, is expressed as an OR between the borrow of xi minus yi, or the borrow of qi minus ti. So understanding the mechanism behind the definition is that one extra step that I think is important in order to do well in the test. Because it's not just the definition, it is why the definition is the way it is that is important. Okay? So then we want to say, well, Tech already showed us an example of how these things can go. So now the question is, how much do I know to come back to infer the bits of a previous column? Okay, so you might want to go through some exercises on your own to basically say, if I know the following bit, okay, the next bit is a 0 already. Okay, so I'm going to demonstrate this. We got x, y, q, t, and d. Okay, so we already know that this is a 0 over here. If I know q is a 1 over here, okay, and this is all I'm given, okay, how much can I infer, of the other bits? In other words, okay, so let's work on this. And Catherine is correct, okay, but I want to show the class here what I mean, by asking this question. I want to determine as much as I can, okay, what is going to be here, what is going to be here, what is going to be here, and what is going to be here. Now, I may not be able to determine every single bit, but I want to push as far as I can to determine those bits. So now the question is, but Tech, you never explain stuff like this in the class, okay? You never explain, how to do this in the class, because I want you to apply what we have learned in class to do this on your own. So let's go ahead and do this on our own, and Catherine is typing. Probably, okay. Okay. All right, so Catherine is going through a lot of mental activity on her own to come up with this conclusion, and she is, well, okay, she was actually incorrect, but she's correct this time. All right, so if we know that there's no overall borrow here, okay, what does it mean? it means that b of x, okay, I'm just going to say xi, yi over here is a 0. Okay, so we consider this to be column I plus 1, and we consider this to be column I. Okay, so we know that the borrow of xi minus yi is a 0. We also know the borrow of qi, ki is also a 0. Why? Because we know ti plus 1 is a 0. So if ti plus 1 is 0, it implies that b xi yi is a 0, and b qi yi is also a 0. Is that okay? This is just looking straight at the definition. If the disjunction is false, then each component of the disjunction has to be false. Does that make sense? But Tech, you never taught us that either, right? But that's not something that I think I should have to teach, because the truth table is already representing that. Okay, so now that we know this, okay, what else do we know? We know that q of I is a 1. Okay, so let me just kind of add to this. So we know q of I is a 1. Now, if q of I is a 1, what can make it happen? Because q of I, after all, is the exclusive OR between x and y. So we know there are two possibilities, right? Because we know x can be a 0, y can be a 1. That will make q a 1. We can also say that, well, but if x is a 1 and y is a 0, that will also make q a 1. So now you have to words are enough. Whatever is more convenient, Catherine. So I will ask for explanation, but the explanation only has to make logical connections to the definitions. And you can explain it in math. You can also explain it in words. Whatever you feel more comfortable about is fine. They just have to be. They just have to make sense logically, and it has to be step by step. So no jumping to conclusion is like, oh, this concludes that x has to be a 1. Okay, well, why is it a 1? It can be a 0 and y can be a 1. But if that is the case, what happens when x is a 0 and y is a 1? Then we end up with a borrow of 1. So it cannot be the case, right? So we just ruled out the possibility that x is a 0 and y is a 1. So now we are locked down to, okay, so if we rule out that possibility, that means the only way left is to have x being a 1 and y being a 0. Okay? Aha. So now we look at t and ask, what can t be? Actually, in this case, I can't really decide what t or d are going to be, because t can be a 0 and then d becomes a 1. That's okay. That's consistent with what is given to you. What about t being a 1 and d being a 0? That is also consistent with what is given to you. So in this case, we kind of have to leave t and d alone, because there's no indication which way they have to go. Okay, that it's not locked down by just knowing that ti plus 1 is a 0 and q of I is a 1. So this is the kind of reasoning that I am expecting people to do during the exam. Okay, you're encountering a problem that you may not have seen before, but being able to troubleshoot and find out how to answer the question. But it's still utilizing the same definitions, the same concepts that we have talked about in class. So are we doing okay so far with what to expect in the exam? All right, cool. All right. So to do well to do well in an exam like this, okay, what needs to happen is a thorough understanding of the concepts. Okay, the definitions is a part of it, but the rationale behind the definitions is also just as important. Okay, why is Q defined this way? Why is T defined this way? Okay, why is the sum or the difference defined in this particular way? The why is the important part. Okay, the definitions you can just write it down. It's open book and open notes. You can just look it up. Okay, but the understanding of these concepts is not something that you can just look up, because it is something that has to be in your mind, during the exam. Okay, So the second thing is you want to be well rested. In other words, spending way too much time the night before to try to cram and memorize things, or worrying is not going to it's not going to help. Okay, having a good night's sleep, having a fresh mind, in the morning is actually really important in a test like this as well. All right. So are there any questions, comments, feedback of any kind? And before we move on and go back to double precision floating point numbers, we got about 25 minutes for that. Okay, we don't have any questions, comments. Okay, you can always direct message me if you don't want the entire class to see, what you want to share with me. Okay, so that's perfectly okay too. All right, so if that is okay, then what we'll do today is to start to talk about the conversion between a base 10 scientific notation to double precision floating point number. Okay, in other words, okay, if I just use my Zerno here, and please remind me to share the Zerno file because I don't mind doing that. I just need to remember to do it. Okay, so if I give you something like, 2.35 E6, okay, that's in base 10. And I say, I want to convert this number into the double precision floating point number format. How are we going to do this? Okay, well, that's what we'll do for today, tomorrow, Thursday a little bit, and possibly sometime next week. So this is going to be a little bit longer topic. Okay, so, and this is also something that most people do not think about, because if you specify a constant like this, okay, let's say in C or C++, you declare a variable, let's say it's x, and it is initialized to 2.35 E6, the compiler would automatically do it for you. Okay, so the compiler is taking a look at the constant, convert it into the double precision floating point number format, come up with the 64 bits that is needed, and copy those 64 bits into the space that it has already allocated for variable x, and that's the end of it. Okay, so all of this stuff is done for you by the compiler. But in this class, in CISP310, we want to understand the process of how to do this, okay? Because that is, once again, applying what we know about the concept about double precision floating point numbers, and practically apply that to solve a problem, which is the conversion itself. Okay, so we want to look into that. So the first thing I want to show you is a program that is kind of done already, and let me see if I still have it where I thought I put it. Okay. This is not the lab for today, so don't worry if you don't have these tools already. This is CodeBlocks, okay, and I'm pretty sure some of you know what it is. It is available for Windows, Linux, and also Mac OS X. It's basically just an IDE or integrated development environment for C and C++. It's open source. It is free to install. And I want to see if I have that project still around. Probably so. There we go. Okay, so this program is kind of partially done. Okay, this function is not done yet. So we are going to have to look at the sources here. And I am parsing it into different portions already. So let me go to the parser. Okay, this is the parse function. And at some point, this file will be shared with you, as one of the labs. So the parse function is basically looking at a string. Okay, the string is going to have something like this. Okay, so this is going to be put into a string as an array of characters, and we want to convert this first into a way where everything are unsigned integers. Okay, because the idea is I don't want to implement something that has to convert from a double into, convert from a string to a double, and I don't want that process to involve calculations using double, because calculations using double are very expensive, especially on architectures where there's no hardware floating point units. So if you're using a Raspberry Pi or if you're using an Arduino, then you might find that those operations are quite expensive, and you can't really just do that. So the first thing we want to do is to represent everything as unsigned. And immediately we have a problem of, well, what about 2.35? That is definitely not an integer, and so how do we represent it? So the way we do that is to say, we just have to unnormalize it. In other words, normalizing is not a good thing, from the conversion perspective. So we look at this as 235. Okay, we just shift the decimal point 2 places to the right hand side. So that is basically the mantissa is now 100-fold of the value that it used to have. So that means I can adjust the exponent to adjust for that. So I can now say, well, it's really the same thing as 235 times 10 to the power of 4, because I made the mantissa 100 times the value that it had. So if I adjust the power of 10 and decrease it by 2, I still end up with the same value. No problem, right? Okay, I'm going to wait for Catherine's question. I would not expand the number entirely because the exponent can be very excessive. Okay, so I'll give you an example. So if I have a 2.35 E60, for instance, okay, there is not enough, I can't expand it because the largest integer you can represent in base as a 64-bit unsigned integer has 19 digits in base 10. And this value over here is going to have 61 digits, right? So it's not going to fit. So that's why I cannot just expand the entire thing. And also, if you expand the entire thing, then you cannot handle negative exponents of 10, because how do you deal with that, right? Okay, so I look at this way. So I have now the mantissa and the exponent of 10. So now the question is, well, if I can give you a program that can convert a value down to this point, at that point, from that point on, how do you convert that value into a double precision floating point number? That is the question. Okay. All right. So what we want to do is to say, how do we express a value? I would still call this mantissa, even though it really should be called a coefficient. But since I have been using mantissa for all the nodes, okay, maybe next semester I can make a consistent change of everything, the notes, the quizzes, the labs and whatnot. But this semester it's a little bit too late, so I will keep calling that part the mantissa. Okay, this is the exponent, but this is the exponent in base 10. So I'm going to call this E10 over here. But what is the value being represented here? The value is quite obviously 235 times 10 to the power of 4, which I can now rewrite as m times 10 to the power of E10. Okay, all I did over here is to substitute actual literal values with the variables that are representing those particular components, right? Okay, are we still good? Kind of looking at a scientific notation and looking at the value that is represented by a scientific notation in base 10. Now, if I say initially, if I say E2, which is the exponent of 2, you go like, what? We don't have an exponent of 2 in this particular representation, but that's okay. I can just say that, well, look at it as 0, okay? So I can now say that times 2 to the power of E2. That should be okay, right? Because E2 is a 0, 2 to the power of 0 is 1, so it doesn't really change V at all. Does that make sense? That I can look at the value of a number using 3 components. So let me highlight which three components we are talking about. The first component is the coefficient, which I also call Mantissa. The second component is the power of 10. And the third component is the power of 2, which initially is a 0. Okay, the exponent of 2 is initially 0. So I'm going to wait for Catherine's typing and move down so that we can have some space ready. All right. Why use 3 in 2 different bases? Okay, so here's the deal. Okay, the deal is I want to eventually, okay, so I want a process, okay, so that eventually I have some m1 times 10 to the power of e10 prime, okay, well, let's call everything prime, so m prime times 2 to the power of e2 prime, where e10 prime is 0. That is the process we are trying to get rid of, okay, turning that component into a 0. So we want to turn e10 into a 0, so that 10 to the power of e10 is going to be just a 1. Okay, so we want to basically remove that component. But in order to remove this component over here, turning this component into a 1, I can play with this as well as this in order to maintain the value. That is the process. This is how we are going to convert a base 10 scientific notation into a quote-unquote base 2 by a representation. Oh, the prime notation just means that it's not going to be the same as m. So m prime does not equal to m. E10 prime does not equal to E10. And E2 prime does not equal to E2. So these are the initial values up here, and these are the final values. That's where we want to go. All right, cool. So let me check the time. We got 10 minutes. So we can work on the fairly simple case first, okay? So we work on the fairly simple case where we have 2.4 E, let's make this easy. Let's make it E, oops, not superscript, E2, okay? So we look at this and go like, okay, so what do we do with this? The first thing is we convert this so that it becomes 24E1, because I'm moving the decimal point 1 place to the right hand side on the Mantissa. So even though it was 2.4 before, now it's 24, and because of that I have to adjust the exponent of 10 so that it goes from 2 to 1. Okay, so now we are looking at 24 times 10 to the power of 1 times e to the power of 0. This is the value that we are given with. So we look at this and go, how do we get rid of the power 10 to the power of 1? We want to get rid of this, okay? We want to turn that into a 0. So people would say, oh, that's pretty easy, right? Because all we have to do is to multiply the Mantissa or the coefficient by 10. So now we have 240 times 10 to the power of 0 times 2 to the power of 0. Woohoo! We are almost done. Okay, not quite done yet, but we're almost done. So we did successfully get rid of the exponent of 10. When I say get rid of, it's turning into a 0. Okay, basically, if it's non-zero, it's still here. Once it turns into a 0, we say, okay, it's gone. Okay, but we are not quite done yet, because now we have a coefficient part that is not normalized, and we know that that part has to be normalized in order to convert everything into a real double precision floating point number. But that process is really easy. Okay, once we get rid of the exponent of 10, the rest is easy. Okay, because now we can look at 240 and ask, what is the binary representation of 240? Okay, so it's 128 plus 64 for sure, because that will add up to 190. Gosh, it's going to be what, 192. And that's room for another 32 for sure. Okay, so what else do we need here? Okay, I need a calculator. I need a calculator myself. So let's see, 240 minus 128 minus 64 minus 32 is 16. Wow, okay, perfect. All right. So we now know that 240 is 1 followed by 7 zeros, but since we also have a 6, so 1 of 128, 1 of 64, 1 of 32, 1 of 16, none of 8, none of 4, none of 2, and none of 1. Okay, this is in base 2 times, let's not even talk about 10 to the power of something anymore because that's gone already. So times 2 to the power of 0. Okay, we look at this and go like, very nice. Okay, the coefficient is in base 2 already, and we only want to adjust the exponent of 2 so that the mantissa is normalized. In other words, there's always an implicit decimal point here, right? Because that's because everything, all the digits are on the non-negative side right now, and we just have to move this point. Okay, let me use a different color to highlight what I want to do. I want to move that over here. Okay, but by doing that, okay, 1.111 in base 2, I have just shifted the binary point 7 places to the left, and every time I do that, the value of the coefficient is halved. I don't want the value to change, right? So every time I move the decimal point to the left-hand side by 1 place, I need to double, somewhere else. Okay. But the convenient place to double, to quote unquote double, is to increment the power of to increment the exponent of 2. So the number of times I have to shift the point to the left is how many times I need to increment the exponent of 2. In this case, it is 7. So we're still doing okay so far with the conversion process. This does require everybody to at least remember, what we talked about last week. Okay. All right. So we're almost done, right? Because now we just have to say, the sign bit is a 0, and then the exponent. Okay. So E2 is 7, but remember the notation. E is the biased exponent, which is an unsigned number. It's biased by 1023. So now we have 1030. So 1030 has 1 followed by a whole bunch of zeros. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, but we have the 30. So this is actually 124 plus 6, which is there's a 4 and a 2 in it. So we have to change. The 1023 is the bias of the exponent that we use in a double precision floating point number. So the E part, the 11 bits for the E part, is a biased value, where the actual value we want to represent is what is in the bit pattern minus 1023. So that's what the 1023 is. It's basically the bias of the exponent. And why is it 1023? Well, don't ask me, because IEEE is what is the organization that determined that the bias is 1023. Why is it not 1024? Don't ask me, because 1024 actually makes more sense. Okay, so getting back to here, I need to make some adjustments because the 2 is corresponding to this bit over here. The 4 is corresponding to this bit over here. So now these two are 1s. And then what is left is the fractional part of the this time normalized coefficient, which are only these 3 bits over here. So we got 1, 1, 1, and then the rest of this are all zeros. So that completes the whole process. The last part, you mean the fractional part of the mantissa? Yeah. Oh, the bias. Okay. So let's go take a look at the definition of double. So double precision float Wikipedia. There we go. And the fractional part. Okay. So when we look at the 64-bit version of this, right there. Okay. Nope, that's 64-bit computing. I want to look at 64 as a double. There we go. Okay. So this is quote unquote the definition. This is the knowledge part of the topic. So we can see how the green part, which is bit 52 to bit 62. So there are 11 bits over here. So those 11 bits, okay. So this is what we call a bias exponent, and it's biased by 1023. So this value e over here is the actual unsigned interpretation of these 11 bits over here. But the actual exponent that we raised to is e minus 1023, and that is by the so IEEE decided that 1023 is the bias that we want to use. So is the bias part okay? The bias of the exponent part okay? It's really just how the number is supposed to be formatted. So if I want, okay, it is a part of a definition, yes. So if I want the exponent of 2 to be 0, then I need to actually specify 1023 in these 11 bits because it's biased by 1023. If the bit pattern represents 1023, it really means a value of 0 for the exponent of 2. All right, cool. So the rest, which is the fraction part, is the fraction of the coefficient part. And we can see how these bits are utilized in both representation. So this is the easier format to see. The coefficient in the binary scientific notation is 1 point. So the 1 point is mandatory. It is always there. But you can see how bit 51, which is this bit over here, it is the leftmost bit of the pink part in the picture. That is the first digit to the right-hand side of the binary point. So that is why I said this portion here is the fractional part of the coefficient of the base 2 scientific notation. Yep, that's a very good question. Okay, Catherine is asking, if 1 point is always there, how do we represent 0? So 0 is one of the exception patterns to the whole thing. If I turn all the bits, okay, from bit 0 all the way to bit 63, if I turn all of those to zeros, then according to IEEE, that defines the bit pattern of the actual real 0 in double. And somebody's going to ask, but Tech, that is wrong. It is not actually 0. It is a very, very, very small value. It is as small as it can get. But it really technically is not the value of 0. You would be absolutely correct about that, okay? But when the computer looks, when the processor looks at that particular bit pattern, it will treat that particular bit pattern as the true value of 0 and not just the closest value to 0 as small as it can get. So does that answer the question, Catherine? All right, cool. So since we are on this topic, it is not just 0 that is special. There's also a bit pattern for infinity, negative infinity, as well as not a number. So on this page, I can now look for infinity. Okay, so there we go. So infinity is specified as this particular bit pattern where we have all ones for the exponent portion and all zeros for the fractional part of the coefficient and a zero for the sign. So this special pattern really is not, if you strictly look at this bit pattern as a value to be interpreted using the early equations, it's a huge number, but it's definitely not infinity. In fact, there's no way to actually write infinity as a number because it doesn't exist. But when the computer or when the processor looks at this particular bit pattern, it will say that, oh, this is equivalent. I'm going to look at this as infinity. So if you try to compare this value to any value that is not infinity, this value is going to be greater than all of the other values. Okay? Now, what if you compare infinity to infinity? I do not know, okay, because that's not supposed to be defined either. You cannot compare infinity to infinity. And Martin was typing a little bit earlier. I'm going to wait for his question. Okay, so let's look at some of the other interesting bit patterns, such as NaN, N-A-N, not a number. So not a number is, oh, okay, Martin is asking, why did you flip the bits with ones in the binary number from the bias? Oh, because, okay, so Martin is referring to these two bits over here, because those two need to be ones in order for the E or the 11 bits to represent 1030. Because E over here, E is the biased version of the actual exponent of 2, so we have to add the bias of 1023 to it, which means we end up with 1030. 1030 is 1024, which is 2 to the power of 10, plus 4, which is 2 to the power of 2, plus 2, which is 2 to the power of 1. So the exponent is telling us how many zeros are after the 1. So we have this one here, which is representing 1024. This one here is representing the 4, and this one here is representing the 2. So that is why I erased the zero, those two specific zeros, and replaced those zeros with ones. So does that kind of answer the question, Martin? All right. All right, so I'm going to wait for more questions. If there are more questions, please go ahead and type. But right now, I need to open up the test or show you the passcode to it because I cannot remember the passcode. Oh, sure. You're welcome, Martin. So let me look at the passcode to today's lab, which is a continuation to talk about floating point numbers. So this time with floating point 2 as a lab, you might want to utilize a calculator or a spreadsheet that can do log. And as I have shown, LibreOffice log can also do log of base 2 right away, which is really convenient. Because with a lot of the questions in this particular lab, being able to take the log with a base 2 is super convenient. Now, if you don't have it, it's not a big deal. You can just take log of 10 or natural log and divide it by the log of 10 or the log of 2 of the log base 10 or log natural log of 2. That will also give you the same thing as log base 2 of something. Right, to show you the passcode. So let's move down to the passcode. Where is it? Oh, right here. So the passcode is just EXP. So let me write it here. There we go. And pin it. All right. All right, so are there any additional questions that relates to the lecture that I can answer now? Because if not, I'm gonna stop the live stream, take a break for about 10 minutes, and then I'll be back to answer questions related to the lab. So I'm gonna wait maybe 10 seconds for questions before I, turn it off. All right. So I'm gonna turn off the live stream now, and I'll be back at about 10:35, and I'll be able to answer questions related to the lab at that time.